Guess what, guys? We're leaving that nonsense behind us now. We're actually going to move on to something that's much more fun. Something that is going to be familiar to you. We're going to go back to calculus and we're going to look at...
Hallelujah!
Okay, we call this general motion in a straight line. So, what have we been looking at? What specific motion have we been looking at the moment? Think about the motion. But what kind of acceleration? Constant acceleration. But do things in real life actually accelerate in a constant?
No.
Remember when you apply the brakes in your car? If you're getting closer and you realize you're not stopping in time, you apply more force, which means your acceleration is changing. Right? So acceleration actually changes constantly. And unfortunately, when we're dealing with these kinds of acceleration, we cannot use these equations that we've been dealing with. Right? So they had to come up with better techniques. And luckily for us, we've already learned these techniques. Okay, so this is actually going to be a very quick walk in the park and just a reminder of what we've been doing before. Okay? So you can have a look in your textbook on page, oh goodness me, I can't give you page numbers, on the previous page. How do objects move when accelerating, when acceleration is non-constant? Okay.
Right next to the rockets.
Oh, so now it's a line.
Right, and on the next page there's a nice displacement time graph.
Okay, what do you have before the general motion in the straight line?
That was the end of the review topic.
Yeah, but just like, and then one more. Ah, that one is at the bottom, and this one's at the middle. Oh, we have figured it out.
I wonder why they have to change it. It's like,
I think it's just like different editions.
yeah, it's still the same book.
Maybe it's not different editions, but it's like, yeah, or maybe it's different batches. Like the one batch, and they noticed that actually, hang on, we could have structured this slightly better, and they quickly like swap something around.
Or it's like a Word document and they just sent it through the email and then
Okay guys, average velocity. So don't get too fancy, think about average velocity. If I gave you a velocity function or a graph, and it was whatever shape, and I asked you for the average velocity,
it's displacement over time.
what kind of displacement over time?
Total.
Change. Yeah? Where did I start with? Where did I end? Okay? So we would say change.
Where did you come from?
There you go. In displacement over change in time. Okay. Now we learned a very special technique where we said, well, if we can take two values that get sort of closer and closer and closer and closer together. So in other words, that they use these Greek symbols, right? Where we use delta for change, right? In displacement over change in time, right? As this approaches its limit. Right? So in other words, if we consider a change in velocity or a change in displacement time, say we have some kind of function like that, and we are looking at the change in velocity because we know velocity is just gradient of a function, right? And we pick 2 points like that, we would get some kind of average velocity. But if we chose a point closer, we'd get an even more approximate. And closer and closer and closer, until eventually what would we get? We'd get the gradient
of a singular point.
at a single point, right? So as this approaches its limit, we get the one that you all know. ds over dt. You've seen this just as dy over dx. That's what you are familiar with. But remember, the variables don't make much difference. That just relates to what we're talking about, and we're talking about displacement time. So, what velocity will this give us? Is it going to give us average velocity? No, it's going to give you the velocity at exactly that point, and we call this instantaneous So the exact velocity at a specific point in time. Okay? So if I gave you a function, what can you do to find velocity?
The SDT.
So we can find the gradient function. So we now no longer have to rely on various equations. If we are given a function for displacement time, we can now use calculus to calculate velocity. Because we know that velocity is just the gradient of displacement time. Right, so in your textbook they've got in the key point, I'm not even going to guess which page it's on. It's 6.2, eh? Will you read that for me, Zara? It says velocity.
Velocity is the rate of change of displacement, and is the derivative of displacement with respect to time.
Change of displacement.
And is the derivative of displacement with respect to time.
With respect to time. Okay, now the reason I'm going to write that as dot 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 is because if you remember back to when we did calculus, if we had dy over dx, we were differentiating y with respect to x. Okay, so if we had dy on dx like that, that told us we are differentiating y with respect to x. In other words, x is the variable, y is the thing that we are differentiating. Okay? So what that tells us is that velocity is ds over dt. The derivative of displacement time is velocity. And actually when we learned calculus, that's kind of what we were alluding to. Right? So we know that if we take the derivative of a function, we get its gradient function. And because gradient of displacement time is velocity, put the two together, we can calculate velocity from displacement time by taking its derivative. So as you can imagine, life's about to get very simple. Do you remember how easy it was to find the derivative of something?
Yes.
Okay? So we might have to brush off the cobwebs from
From the brain.
5 weeks ago. And we don't mix up.
5 weeks ago.
We don't mix up. Yeah, I actually had to go and look how long ago we did this.
Oh, wow.
Oh my word. 5 weeks.
Okay, Zara, will you read the question of work example
6.1.
6.1?
A particle moves in a straight line so that its displacement S(m) at time ts is given by S equals to t cubed minus 14t.
T cubed minus.
14t.
Okay.
Find
So-
an expression for its velocity at time t.
At time t. Okay, so if they say at time t, that just means find me a velocity function. Okay, so here we have a displacement time function, and they want us to find some velocity function, right? So find me a function that gives me velocity. So what do we know about velocity? Velocity is equal to change in displacement over change in time. But don't we remember that shorthand notation? That just tells me to find the derivative. So what's the derivative of that? So let's unwind the cobwebs. We're finding the derivative, not the primitive, so we need to differentiate. So do we multiply or do we divide? What do we do here? We multiply by the power. And then we
Square.
reduce the power by 1. Okay? The next one, we multiply by the power. What's the power over there? It's 1, so this is just minus 14, and we reduce the power by 1. So 1 minus 1 is?
1. 0.
Zero, zero.
Zero.
It's the power of 0 is 1.
That's how you
So-
get it,
This is my velocity function. So I have a displacement function. I just differentiate, I get a velocity function. Now, very importantly, this is a velocity function. And what is velocity calculated in? Velocity is
meters per second. Sorry.
meters per second. Okay? So if they ask you for a velocity function, you have to differentiate, but you also have to specify that it's in meters per second. Easy. Now if I gave you time 2, you could tell me what the velocity was. Isn't having an equation just so much nicer than guessing stuff?
Oh, it's wonderful.
Yeah? So, if you thought the last chapter was quick, you will be surprised at how quickly we will get through this chapter. Okay? Because you've actually done all the difficult work already. You've learned to integrate and you've learned to differentiate. And now we're going to use those in
Only
practice.
two chapters.
We're maybe done with chapter 6.
Okay, so the next one is basically exactly the same. Remember, when we are considering things in general motion, we're only going to consider them in a straight line. Because I think you guys have done some circular motion. Not yet. Are you going to do it?
I think so.
Okay, you'll see it. If you carried on with mechanics, we would continue with circular motion, and that's where things get really interesting. So we're only going to be considering things moving in a straight line.
So, at the end of next week, are we going to be done with chapter 6?
Basically,
I think it's like in, like what we were talking about yesterday with guitar string. She actually taught me guitar
I
string.
guess it's safe to say that mechanics
Not just
now looks like maths again, and not physics.
yeah, well, we're going to the pure maths now. I'll link a video. There was a guy that I love watching, Eddie Wu. He actually just started mechanics now, and he said, if you really want to see the difference between physics and maths, physics is all about how do you prove something in physics? What do they do to prove something?
Thank you, suffer.
Lots and lots and lots of experiments. What do mathematicians use to prove something?
Equation.
Logic.
Yeah.
Yeah? So there's that was his like, those are the main differences. In physics, they do lots of experiments. I mean, they've got logic, but they're not satisfied with that.
No.
They have to prove it by experimenting. Whereas mathematicians are, you can prove to me, you can experiment 1,000,000 times that a triangle adds up to 180 degrees. That's not good enough. Show me the logic. That's the difference between maths and physics. Which one do you think is more sound?
Maths.
That's a debate for another day. Okay, let's not get the city again arguing us like he's going to hear us.
Imagine as if you like open up the door like, what are you guys
Right,
talking
just give me
about?
the function. We have a displacement function of
2t cubed
2t cubed
minus 10t squared.
minus 10t squared. So this function tells me displacement. This object moves according to that function. Okay, which means that I could calculate its displacement. If I gave you time 2, I could actually work out what its displacement was. Remembering that displacement is position. Okay? But they want us to find the
Speed when t is 2.
speed.
Mr. Jane,
Yes,
what are these funny lines here?
I'm going to get to that in a second. When t equals 2. We haven't actually learned those yet, but I will touch on what they mean. Okay, speed is the same thing as
Velocity.
velocity. Okay? So if I want to find speed, I have a displacement function, so I can just find its velocity function. So I want to find v, that's just ds over dt. That means I need to differentiate. Okay? The reason I'm saying you need to write this is because if I gave you the velocity and I asked you to find the displacement, you would have to integrate to go backwards. Okay? So here are the ones that you're going to have. Displacement time, velocity time, acceleration time. Yeah? Those are the ones we've dealt with. All of them we measure in meters or meters per second. So here we're going from meters, meters per second, meters per second squared. And if we could actually carry on, we'd get meters per second cubed, but there's no such thing. Okay? So if I want to go from this one to that one, or from that one to that one, I differentiate. Oh, no, right, that's too long. And if I want to go backwards, what would I have to do?
Integrate.
Integrate.
And differentiate.
anti-differentiate. So you need to just remember the order that you're going. Think about the function you have, where are you going, which process do I need to look at. We're going to look at all the processes, but for now we're just looking at going from displacement to velocity, and fortunately for us that just means differentiate. Okay, quickly differentiate for me, Trey.
Which one? Oh, the ds over.
Yeah, so find me the velocity function quickly. So differentiate displacement for me.
Okay, that's. Do you add it to? Oh, you minus it. No.
We multiply. So we multiply the power down, so we get 6.
6t
And reduce the power by 1. And then we
minus 20t.
That's it. There we found our velocity function. So we just have to rub the cobwebs out of our differentiation toolbox.
Yeah,
okay?
I was like having
Try to think, yeah, do we go backwards, which way? So try to get in the habit of remembering.
Forgot the feather duster, just take
Okay,
a little
at what time did I want to find velocity? Okay, so we'll say when t equals 2, velocity is equal to 6 times 2 squared minus 20 times 2. That's equal to, that's 4 times, that's 24 minus 40, so minus 16 meters per second. Can speed be negative? Speed. Speed has only got magnitude, no direction. That minus sign is a direction sign. So do we care about it when we're talking about speed? Right? That's why they say speed is equal to, now you're probably wondering what do these straight lines mean? Okay? Those straight lines are absolute value lines. When we talk about the absolute value of something, we're saying everything on the inside here, whatever comes out of it, just make it positive. If I put a minus 4 like this, what's the answer? 4. If I take the absolute value of 4, what's the answer? 4. Okay? Anything inside there just becomes positive. That's what absolute value means.
Why don't they just say absolute value?
Because the right absolute value takes up space. That just says absolute value, make it positive. Okay? Something we will do next year if you carry on with A-level maths. Okay, so if my velocity is 60 meters per second, what's my speed?
16.
Yeah. Speed doesn't care about direction, it's always positive. Equals 16 meters per second. So you need to be very careful when you read the question. If they ask you find velocity at time 2, then you need to include direction. This thing here, that's just direction. In other words, if I said that going that way is positive, in which way are you going? I'm saying positive going in that direction. This guy's actually going, he's going that way because he's going in the opposite direction. That's all the velocity, the direction means. And who sets direction?
We do.
You can set direction. You can decide which way you want positive and negative to be. Okay, so alright, the last one. Let me quickly just see how bad this is going to be. Okay, this is a fun one. Okay, this is one that makes you think a little bit.
S equals 2t cubed
2t cubed,
minus 12t squared
yeah?
plus 18t.
Okay, that's a displacement function, right? So, what does the question ask us? It says a particle moves backwards and forwards in a straight line according to that function. Okay, that function will tell you how much displacement it has in time. Okay? And then it says find the distance it travels after 5 seconds. So, distance after 5 seconds. So, if Bob was here, what would he tell you to do? Bob's not very good at maths. I mean, he's only good at standing in lifts.
Oh, I thought you
Maybe
meant
Bob-
Bob Senior. Maybe
Bob
Bob
is special.
Senior, rest in pieces.
Okay? So Bob would probably say, aha, displacement, awesome, let me pop T into there. So that's what we're going to do. So displacement equals 2 times 5 cubed minus 12 5 squared plus 18 times 5, and that's going to give you 40, I believe.
Yeah.
What does that 40 meters represent? Is that how much this person has traveled in distance?
No, it
Okay.
is how far it is from point A to point B.
So the easiest way to explain this to you is, there's a hill. Here is Bob Jr. And Bob Jr. walks up the hill. Okay? This hill is 50 meters from the bottom to the top. What is his displacement?
Whatever the thing at the bottom was. Whatever this is at the bottom.
Well, this is the starting. I'm going to set this as position 0. That's the starting location. He's gone from there to there, so his displacement is?
Not 50.
Yeah. He's moved up the hill 50 meters. He's gone from there to there. He's 50 meters away from where he started. How much distance did he travel? He's also traveled 50 meters. So here, my displacement and my distance are exactly the same.
But if he's zigzagging,
Okay, now. Ooh, that's a bit of a steep hill. Poor Bob. Maybe that's how you roll down the hill. Okay?
He went up to
Therefore, he was up at the top of the hill, right? That was his first journey of 50 meters. And then he saw what he could see, and then he came back down the mountain. So here he is on the bottom there. He has come down the hill to where he started. So he's exactly where he started. What is his displacement?
0.
Yeah, his displacement is 0. So you might think he hasn't moved at all. But actually, how much distance has he traveled?
100 meters.
100 meters. Do you see the vast difference between displacement and velocity and distance? Okay? Displacement is just telling you a position. Right? It tells you position relative to a starting location. So he has moved, in this example, 0. Because he's right back where he started. And here, he's 50 meters away from where he started. Okay? Now, logically, if he's 50 meters away from where he started, how much distance must he have traveled to get there? If you start at 0 and you end up 50 meters away, how much distance have you traveled? 50 meters. Okay? So we need to use some logic to calculate distance. We can get distance from displacement, but we have to be a little bit clever with the way we do it. Okay? So, does this 40 meters represent how much he's traveled? No. Okay? Because this function, right, it even tells you he could have been moving backwards and forwards. In other words, if
Displacement.
right, he could have been going in this direction, and then he could have going in this direction. Then he could have going in this direction, and he ended up in some position. Now, it's just going to tell you how far away he started and where he ended up. But it's not going to tell you all the in-betweens. Okay? But the nice thing is, what changes when somebody changes direction? Not the speed always stays the same. The velocity. This way velocity is, and now what am I right at this very second?
0.
Stationary. And then I go this way, it's negative, and now I need to be stationary before I can turn around. What have you learned about stationary things? What can we do?
We can find the stationary points.
There we go. So we're going to find the gradient function, right? Because where this thing is stationary is where velocity is 0. When you turn around, your velocity has to be 0 for a split second before you go in the opposite direction. It would be nice if you could instantaneously turn around, but you can't. Right? So it has to be a gradual process. So we're going to find the velocity function, and we know velocity is just the derivative of displacement. So Dominic, your turn. You can differentiate that for me.
Wait, hang on, what am I differentiating? The top one.
Yeah, top one.
Oh. Yeah, 6t squared minus 24t. That's it.
Plus 18.
Oh yeah, 3
That's
pieces.
Okay?
It's 1, not 0.
So this is my velocity function. What am I interested in finding? I want to know where velocity is. 0, because that's where I've momentarily done my little turnaround. Okay, and that'll tell me exactly at what time I've turned around as well. So let's make that v equals 0, because that's my turning point. My velocity is 0, and 60 squared minus 24t plus 18.
We're gonna have to remember Charlie somehow soon, won't we, again?
It's coming. Although even motion has a clever way of kicking Charlie to the curb and saying, "Go away, Charlie! Down, boy!"
Nobody likes Charlie.
Okay.
No one likes him.
What can we divide this to make things easier?
By 2.
Even easier. They're all
Oh,
divisible by 6. So we have t squared minus 4t plus 3 equal to 0. This looks like a very easy thing to factorize. Minus, yeah. So t equals 3 or t equals 1. So that tells me at 1 second is where my first change in velocity happens, and at 3 seconds is where my next change in velocity happens. So how can I calculate how far I've traveled with these times, knowing that I changed direction at these 2 times? And knowing that I've only got a displacement function to work with. I don't have some distance function, I've only got that displacement function.
Well, you also need to know whether you are negative or positive at those points, so you can take.
You could, that's actually a good point. Which direction am I traveling? You could take what to find that out?
Second derivative.
Second derivative. Okay? Remember, it will tell you if it's positive or negative. But we don't have to get that deep into that for this example. If I calculate my displacement after 1 second, won't I have the distance for that first second? Because remember, for the first second I'm going in one direction. I'm only changing after the first second. Yeah? So I'm interested from time equal to 0, I'm traveling in some direction. But remember, at the end of the day, the distance, I don't care if I'm going backwards first, and then forwards, and then backwards. I'm actually just interested in calculating the distances. So here I start at 0. At time equal to 1 second is where I stop before I turn around. So why don't I just calculate my displacement here? So we'll go back to our displacement function. S equals, well, 2 times 1 cubed minus 12 times 1 squared plus 18. That's going to give me 2 minus 12 plus 18 is 8 meters. So how far have I traveled in the first second? If my displacement from 0 to 1 is 8 meters, I have to have traveled how far to get there? 8 meters. Right, so I've traveled 8 meters in the first second. Right, what I can do now is, let's see where my displacement is after 3 seconds. So displacement equals 2 times 3 cubed minus 12 times 3 squared plus 18. Guess what that's going to give you? 0. Where am I after 3 seconds? Not distance. Where am I in displacement terms? Where am I after 3 seconds?
0. So
Right back where I started. How far did I have to move to get there? If I started 8 meters away and I'm back where I started, how much did I move? I had to have moved 8 meters. Right? There's no other ways I got 8 meters back there.
But you weren't walking fast.
Well, we don't know. We could actually find the instantaneous velocities at any point in there with this function.
Well, I mean, you were walking 1/3 of the speed that you were the first time.
Right. Now we have that last 2 seconds. Do we have any more changes in direction after that? No. We have one more change here. We changed direction at 1 second. We changed direction at 3 seconds. And now for the rest of the journey, we're only going in one direction. If I was not going in one direction, I would have more stationary points. There would have to be more points where I turned around. But I know from this function, there's only 2. So here's from 3 to 5. Right, I'm at 0 at the moment. After 5 seconds, we actually calculated it already. Where was I after 5 seconds? I was 40 meters away. So how far, if I started at 0, how far did I have to travel to get 40 meters away? Well, I have to walk 40 meters to get there. So you have to take these problems one step at a time, and it helps to draw a little diagram like this to explain to yourself what's going on. Where am I? But you could have walked back, but maybe you only walked back half the distance. That's your new starting location. And then based on that information, you've got to think, where did I end up after 5 seconds? So what's the total distance this guy traveled? Can we just add them all up? 8 meters plus 8 meters plus 40 meters, that gives me 56, 12 meters. 12 meters. So how far did Bob Jr. walk? 56.
6 meters.
Is that
Bob Jr. is fit.
He is
And 12.
very fit.